Hey guys, it's me again. We're going to finish up this lesson. We're going to do it in two parts, two videos today. The first part we're going to talk about just kind of the notes, and then the last part we're going to go through those problems that were at the end of this particular lesson, okay? And so the first part we're going to talk about is stoichiometry. I know we talked about it quite a bit in chapter 9, and some of you guys understood it pretty well, and some of you guys still had a hard time. It's still here, and I told you that was something that we were going to do in chapter 10. But it's the same way that we approached it in chapter 9. We're going to do the same thing in chapter 10. We have to have a balanced equation. Feel very confident that you guys all know how to do that. And from that, those coefficients from the balanced equation gives us our mole ratio. In chapter, or earlier in one of a previous lesson, I informed you or told you that Gay-Lussac's law of combining volume dealt with the molar ratio. And that's kind of where we were going with that, and now we're actually applying it. So let's take a look at this example problem. I have 2 moles of calcium reacting with water to form calcium hydroxide, and what is the volume of hydrogen gas that will be produced at STP? Now, typically speaking, you would only get this information on a test or a quiz, and you'd have to kind of come up with that equation and then, of course, balance it. The nice thing with your notes, I already gave you that information, but I know calcium and water, H2O, calcium plus water, those are going to be the reactants, and it's going to yield to form calcium hydroxide. All right, and that's CaOH, excuse me, and a 2 on the outside because calcium has a +2 charge and the hydroxide ion has a -1. All right, and then of course hydrogen gas. I know hydrogen is a diatomic element or molecule, and so that's why it's H2 listed here. All right, and I know it's a part of the product because it's asking how much or what the volume would be for that particular gas. All right, and so now I look at my problem and I start off with that 2 moles of calcium, and I have to use that information and look at the molar ratio in the balanced equation to get from the calcium, the number of moles of calcium to the number of moles of hydrogen. The nice thing here is that it's a 1-to-1 ratio because there's a 1 in front of calcium, or there's no number, so it's understood to be 1, and there's also a 1 or understood 1 for hydrogen. So that's, like I said, a really good thing. So the moles of calcium would cancel out in this case, and I'm left with moles of hydrogen. Now, some of you guys may think, okay, great, I have the answer, it's 2, so that's wonderful. That's not what the question is asking. It says, what's the volume? The fact that it's at STP, I know I'm going to have to use my molar volume conversion factor to go from moles to liter. And so when I put that in there, my moles of hydrogen will cancel out at this point, and I'm left with liters of hydrogen. All right, and so then it's just a matter of math. The 2 times 1 divided by 1, but again, this cancels out, so you really don't have to do this step, but times 22.4 liters, and that gives me an answer of 44.8 liters of hydrogen at STP. And again, you must include the at STP part because under different circumstances, that's not what you would have. All right, so that's very important. So that's how we would use the stoichiometry as it relates to gases, okay? Let's look at another example, another practice problem. I know it says to try. That's not necessarily a left side activity, but if you wanted to put it on the left side, it's fine, but you don't have to. The question says how many milliliters of propane, and I gave you the formula, must be burned to form 100 mils of carbon dioxide. Again, I have given you the equation, so I'm starting with propane. And I have oxygen because it's a combustion reaction, and my products are carbon dioxide and water. Okay, and so again, I went ahead and balanced that equation for you. So all I have to do now is start with what I've been given. I have 100 milliliters of carbon dioxide right here. All right, now the problem with this particular problem, and you'll notice that I converted it to liters. The reason I did that is because my molar molar volume is moles to liters, and so I needed this to be in liters before I could do anything. All right, and so that's the reason why it's 0.1 instead of 100. I just moved the decimal 1, 2, 3 spaces to get to 0.1. All right, and so then from there, I'm going to use, like I said, the molar ratio, molar volume, excuse me, and my liters are going to cancel out of carbon dioxide, and I'm left with moles of carbon dioxide. Great, but not what I'm looking for. I need to then look at my balanced equation. How many moles of carbon dioxide do I have compared to the moles of the propane, C3H8? All right, and this is a 3-to-1 ratio when we're looking at carbon dioxide compared to the propane. So my moles of carbon dioxide will cancel out, and I'm left with moles of C3H8. But again, the question is asking me something in volume as it relates to volume. And so that's not my final answer. I need one more step. I'm going to have to use this lovely conversion factor one more time to get from moles of the propane to liters, or some unit of volume. And when I do that, my moles cancel out and I'm left with liters. So now I just do the math. 0.1 divided by the 22.4, because it's at the bottom, divided by 3, I don't really have to multiply by 1, times 22.4 gives me 0.033 liters. Now, under normal circumstances, many of you guys would just say, okay, great, I have the answer, I'm done. Notice what I'm asking, how many milliliters? So then I have to take this number and convert it back to milliliters. And when I do that, I just move my decimal 1, 2, 3 places. So my final answer would be 33.3 milliliters for the propane. All right, and I needed technically four sig figs, and so this technically would be minus 1 point. Shame on me, but I would need 4 sig figs because I have 4 sig figs here. You never use the conversion factors to determine sig figs, and you don't use the temperature as I stated before. All right. Let's talk a little bit about the ideal gas laws, and this is my favorite gas law of all of them, so yay for that. The ideal gas law, the idea is that the gas is supposed to be perfect. It's supposed to, all of the kinetic molecular theory that we talked about at the beginning of this chapter should actually follow that, all right, based on the kinetic molecular theory. Now, the problem is we don't have any real world gases, so that's the issue there. But we like to use the ideal gas laws. But in order to use it, we have to assume a couple of things. And again, going back to the kinetic molecular theory at the beginning of the chapter, that the gas particles are tiny compared to the distance between them. That was one of the things we said. It does not match for real gases, which makes sense because if it's an ideal gas, we would have to assume that this wouldn't be true for real gases, right? Because then we wouldn't need to worry about it. High temperatures and low pressure makes it valid, and so we have to have that. But with the high pressure and low temperature, we have a liquefied situation, so those gas molecules are actually going to slow down from the gas to become a liquid. That's basically what that's saying, okay? All right, and so the equation for the gas law, it looks complicated, but it really isn't as bad. It's PV equals nRT. Now let's identify those particles or those parts of that particular equation. P is going to be your pressure, and your pressure could be in torrs, atmospheres. It could be so many different things. Your volume, typically you want it to be in liters, but again, it could be in different things. You'll just have to convert it. Your N, your number of moles, that's something that we haven't incorporated this entire time. Everything else, we've held the number of moles constant in all of the 4 previous types of gas laws. This one, we're actually incorporating it. And your number of moles, the unit will be moles. All right. And then your R. This is the thing that's going to be a little challenging for some of you guys. The R is a gas constant, and with that being said, the number is the same every time. However, because you can have a different pressure, your gas constant can be different based on the pressure situation. So in one scenario, your R could be 0.0821 liters times moles, liters times atmospheres per moles Kelvin. Notice that pressure here is atmosphere. If I had a pressure that was in torr, my value for my gas constant's value is a little different. It's 62.36. And then finally, if it's in kilopascal, it's 8.31. Now, if any of you guys are going on to study chemistry in college, you're probably going to use this one more frequently than any others. But I typically will provide the gas constant value for you, especially under these circumstances. Normally I wouldn't, but you guys will be provided that information. You just have to know which one to use at what time, okay? And this is a unit. This is not to multiply. Sometimes in the past, I've seen people trying to use this number, then multiplying again. Don't do that. It's literally there to cancel out some things, and I'm going to show you in just a moment. And then, of course, your T is your temperature in Kelvin, as we've stated before. All right, so let's look at this example. The question says, how many moles of gas are present in 2.4 liters in a 2.4 liter sample at 1.25 atmospheres of pressure at 27 degrees Celsius? So we know our pressure is 1.25 atmospheres. I don't have to worry about initial versus final. This is what it is. The volume is 2.4 liters. The number of moles, that's what we're looking for. We're not really sure. And our R, in this particular case, we're going to use 0.0821. The reason why is because this one has a unit that includes the ATM atmosphere. All right, because our pressure is in atmosphere, this is the gas constant that we will need to use. And then our temperature is 27 degrees Celsius, but I added 273 to that to make it 300 Kelvin, and that's going to be our working temperature that we use. Because I'm looking for, I'm using this equation, PV is equal to nRT, and I need to get N by itself, I would divide both sides by RT to get a working equation that looks like this. N is equal to PV over RT. So now I just plug in my numbers, my values for that, and you'll see I have my PV RT right here. Now this is the part that I said you have to be very careful about, because we're only using this information to cancel out certain things. My atmosphere, cancels out. All right, my liters cancels out. Notice I'm not multiplying anything here. I'm just using it to cancel out things. And then, of course, my kelvins will cancel out. I'm left with the unit of moles, which is great because I'm looking for number of moles. In the calculator, 1.25 times 2.4 divided by 0.0821 divided by 300, and I get the answer. That is a big number, this really long number. I look at my original problem, I have 2 sig figs here, 3 here. I don't use temperature to determine sig figs, and so my final answer should be to 2 sig figs. So ultimately I have 0.12 moles in this particular case. So that's how we do those, and hopefully you will enjoy the practice problems. All right, I'm going to stop the tape here, and I'm going to come back with the second one, okay?